All right, hello everyone. Welcome back to Machine Organization and Programming. We've got lecture 21 today. I did manage to get almost all of my prep work and lecture notes prepared on Saturday before I had to head out, but I didn't get a chance to do any of the recording, so I'm working on that right now. Just sorry for the delay, guys. It looks like I'm about one business day behind the schedule at this point for my lecture video production. Hopefully we'll be able to get caught up relatively quickly. A couple of announcements. Quiz 5 is available now. It'll be available till Wednesday at midnight. And we will have one more quiz next Monday covering the dynamic memory allocation and cache memory stuff from this coming week. All right. The lecture schedule looks like we have 7 more official classroom lectures worth of material after today. This might not translate directly into 7 videos. If it does, then I'm hoping to release them, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and Monday. That gives you guys enough time to watch them. And then we've got the final exam next week. So there'll be a couple of days as a buffer just to get caught up, make sure everything is going well. From my point of view, releasing 7 videos in 7 days, looking at my past history is an aggressively optimistic goal for me. I do have a pretty open week. I've got a date on Friday night. My son's testing for his black belt in karate on Saturday, so there's not a whole lot filling up my week. It's possible. I might be able to do it. All right, like I said, our final exam is actually going to be available a week from Thursday in the morning. I'm still waiting to hear back from the registrar about when final grades are due. I believe it's Sunday evening, so we'll probably keep the exam open through Saturday at some point, and that'll give everybody 24 hours to submit regrade requests. It'll be the last thing on my list is the regrade questions from the final exam. So hopefully that will go well. All right, let's see. Project-wise, Project 4 is due on Thursday of this week. Several people have turned it in already. I think it's a really fun one. I hope you guys enjoy it. We'll be releasing Project 5. This is our last project. We're only going to do 5 this term, and the original plan was to do 6, but we're merging projects 5 and 6 into just one project and toning it down so that it's not overwhelming right at the last week of the semester. That should be coming very in the next few days. It's going to be due a week from Thursday also. We'll get it out as soon as it's ready for you guys. Let's see. Regrade requests. This is a midterm regrade requests. I've gotten through about half of them. I did most of them right as the midterm was occurring. And then since then, I've been prioritizing getting the lectures ready, answering all the questions about course content, homework questions. And I've really put the regrade requests on the back burner. So I'm sending people emails as I get to your regrade request, just so you know that it's been dealt with. If you've not gotten an email from me, it's in my list. If you send me an email or you put it on Piazza, I've got it flagged and I'll get there. But I'm going to prioritize these other things over regrade requests. And it might not be until the very end of the term when I finally go through all of them and give you guys your extra points back. And finally, last announcement, course evaluations, I believe, came out today. Normally in a real lecture class, this is the day that I would bring candy and claim that it's absolutely not a bribe. Why don't you fill out your evaluation while you're enjoying some chocolate? So here's what I want you to do. I want you to go get your own candy, kick back, enjoy some chocolate, think happy thoughts, and then go fill out that evaluation form for me. All right, I'm just kidding. I'm just messing around. But yeah, I actually really do value all the feedback I get about the course. People have been leaving comments on YouTube videos. People send me emails. I've taken all of those into consideration. The things that I know that I could do better on is sticking to my schedule, my video release schedule. I got behind when I got sick, and I know it bothers me. But if there are some other things that you guys think I can do better, I would love to hear it. Particularly, this is really my first online course that I've ever taught. So if you have some feedback about things that worked well in the online arena, I'd love to hear it. I think the office hour thing worked really well compared to what I did in the past. But if you've seen better systems, I'd love to hear it. Yeah, just any feedback you guys have about how to make this course better next time through would be fabulous. All right, then. So today's lecture, as far as content goes, we're going to be talking about arrays, structures, and security, and wrap up this all of chapter 3 at this point. C uses a really straightforward implementation for arrays, and that makes translation into machine code very straightforward. Basically, it gives us a lot of freedom. We can generate pointers to any element in an array, and some of the things that make this a little tricky are that the compiler is really good at shortening up the calculations of addresses and taking little shortcuts. So it can make the assembly code really hard to read to figure out where is this addressing, in which element of an array is this really getting at. So what I want to do today is sort of take more of an experimental approach rather than just putting a whole bunch of content up there on PowerPoint slides. I want to go generate some code, look at it, and just kind of poke at the assembly, see if we can figure out what's going on. So more of an experimental, let's try this, let's test that, let's see where things are. Because this is really kind of what you guys are going to be doing for the homework assignment for this week. The P4 due on Thursday. And in the past, when I have used these tools, when I go and start digging through the assembly code to figure out what is going wrong, or how can I make this go faster, this is usually the approach I take, is to just set up a little test case and do a little experiment. I think the other way that you might run into this is if you're trying to look at some competitor code and like break down what it's trying to do. In that case, it's a little different. You'll be reading straight from the assembly. You won't be having the C code there translated into assembly to see what the compiler is doing. But for this week, I want to go with that experimental process. All right, so let me jump over onto CSL Machine and I'll pull up my very first experiment. All right, guys, so I got my first example pulled up here. The only thing this code does is allocate space for an array, int A, with 5 elements. And then it's going to fill in those elements with 10, 20, 30, 40, 50. So I'm just going to go compile this, come back, and then we'll take a look at the assembly, see what happened here. All right, I just want to point out I did use some compiler options to simplify that assembly code. So calling GCC with the -s, so it stops after the assembler on the function on the file array1.c. I'm using M32, so just like every other compiler command for the entire course. Taking out the asynchronous unwind tables, FNOPIE, and the stack protection. We'll come back and talk about stack protection at the end of the course under security, or at the end of the lecture today, part of the security. But this will simplify the assembly, and we're just going to get the x86 instructions. Vim with the -O will open up multiple files, and I'm using array1 with the wildcard star to get the array1.c and the array1.s that was produced by this compiling. Okay, let me do that now. All right, so here we go. Pretty straightforward. Let's see here. Push the base pointer, do that stack management stuff. So store the stack pointer in the base pointer. And then right here on line 9, we've got assembly code for allocating space for this array. Right here I've got 5 integers that should only take up 20 bytes. But the way x86 works, it likes to have stack frames be nice, even like blocks of 16 bytes. So it will actually reserve more space when it reserves space for things. And it's going to waste a little bit here. Part of that is done for alignment reasons, because then the CPU can optimize memory fetching much more quickly. We'll talk about that and probably later on in this week. Okay, and then it looks like we're just moving immediate value 10 into a memory location, 20 into a memory location, 30 into a memory location. All right, piece of cake. So, and then this line 15 is getting ready to return. So this section right here is the important stuff about arrays. I'm going to pause for a second and just over here in this space, draw a picture of what's going on in memory so we can talk about this. One sec. All right, so I real quick just sketched in what's going on in memory. So at the very bottom of the stack frame, I've got the base pointer where I'm storing the old base pointer from the operating system, so it knows where to go back to. And then I've reserved 32 bytes worth of data. I've just blocked those off in 4-byte chunks because integers are 4 bytes. And then we're going to be moving, let's see, the very next thing we do is we move the immediate value 10 into this -20 position. So right there is -20. I'm going to store 10 right there. And this is A0. Whoops, just like that. Next thing, I put a 20 at 16. So this is a 1. All right, and so on. Let me just fill these in, and I'll be right back. All right, so I got the rest of those filled in, 10, 20, 30, 40, 50, in positions A0, A1, A2, A3, A4. And just one of the things I wanted to point out here is that the very first address that's being used is the one with the lowest address. It's got the lowest number associated with it. So 20, here in this case, above the base pointer, is going to be the lowest address. If it were something like OX 100 or something, then this would be at OX 104, 108, 10C, and 110. So lowest address is where the very first array element is stored. And then it's just a contiguous block of memory that's been reserved, and all of the elements are just stored in there in sequence. All right. And I hope I just want to like point out too that right below this we would have stored the return value. And one of the reasons that writing out of bounds can be so dangerous, and this is the security part I'm hinting already, is that if I were to write to A5, I would be writing over the stored base pointer for the operating system stack frame. And if I wrote again to A6, I'd be writing over the return value. So that's going to crash everything. All right. Next up, I'm going to change this example just a little bit and turn it into a different file. Example 2. One sec, let me pull that up. All right, I'm back. I just made one little change here. Instead of using an integer array, I'm now creating a character array. And I'm sticking in CS354 and a null terminal. So this is a string in C. And then if we take a look at what is generated in the assembly, the important lines are right here. So above that, we've arranged for the stack variable, stack register pointers for the base pointer and the stack pointer, right? And then here, we're only reserving 16 bytes. Let's see here, 1, 2, 3, 4, 5, 6. I really only needed 6, but x86 likes to reserve things in nice, even blocks of 16. So it's taking care of that. Reserve some extra space. It's wasting a little bit. The next thing we're going to do is see that all of these characters have already been translated into ASCII and then moved into their respective positions. The only one I recognize without going back to look it up is the 0 here, and that is for the null terminal character. So we see is that, I need to change these numbers because now I don't have integer sized bytes. These are individual bytes. This is 1 away from the base pointer, 2 away from the base pointer. Hold on, let me go change those numbers. Okay, got my numbers changed, and I put in the data. So we can see that here at position 1 above EBP, I'm storing the value 0. That is the null terminal. If you guys want, you can go back, pull up the man page for ASCII, just man space ASCII from the terminal, and it'll give you the list of all these codes. You can see that number 52 is the corresponding to the number 4. 53 corresponds to the number 5. 51 corresponds to number 3, and so on. And these, again, are just stored in order with the very first element of the array at the lowest possible address. And we didn't save any extra space. The very next thing is the base pointer on the stack. All right, so what I want to do here is just real quick take a note and just say that when we allocate, insert. When we allocate things, what we're going to be looking for is how many bytes does this take up? How much space do I really use? How much do I need? It's just the number of elements times the size of the element. So pretty straightforward. There's some example questions in the book that dive into this a little more and give you some like tricky ones. This is one of my favorite. Don't get caught by this one. Give this some thought. How much space is required to store this array? It looks like it might be 8 because I see that character right there. But this is actually an array of pointers to characters. So each one of these elements, I'm going to have 8 elements, and they're all going to be pointers to characters. And a pointer takes up 4 bytes. So this one is tricky. This one is 4 times 8. 32 bytes are required for this. Something like this array right here, character is 1 byte. I've got 6 of them. 6 times 1 is 6. pretty straightforward. The integer array I had 5 integers. Size was 4. I needed 20 bytes. It actually reserves more for alignment, but all right. So the next little trick is, where do we find each of the elements? So each one of these things has a very first address where element 0 is in the array. And in this case, for the character version, all right, got my typing glitches fixed. Sorry about the little distraction there. Text changed a little bit. I want to ask the question next, where is element AI? And the answer is pretty straightforward. We're going to have a base address where we've got element A0 stored, first element in the array. And in this case, element 0 is stored at one address above EBP. So -1 EBP is going to be that base address. And then for every other element in the array, if I'm looking for element I, for example, I could be the 4th element. I need to take that base address and add the size of the element times how many are moving. So in this case, it's going to be, so if I want to find out where A4 is, then all I need to do is look up the starting address, one off of EBP, and then I'm going to add to that 1 byte times 4, my I right here is 4. Characters are 1 byte. If this were the integer array that I used in my first example, this 1 would be replaced with a 4 because integers are 4 bytes. All right, I'm going to write some code that actually causes the compiler to generate code that does it, this calculation for us, and we'll take a look at it. One sec. All right, guys, I put together an example that I thought would be perfect for demonstrating this, and then was surprised to what I got. So check this out. I just took my code from the very first integer array and just added one line to it, int I equals A0. I'm just going to have it access this, store it somewhere. I can't take one memory place to another memory place directly. I've got to load it into a register, so I thought this would be interesting, but not in the way I expected. So check this out. This was the old data map that I had for the stack. I have that first element at position 20 above the base pointer. It's shifted the whole thing. So now position, the very A0 is now at position -24. So it moved up 1. 20 moved up 1, 16, 12, and 8. And then what it's doing is this int I value is actually being stored at 4 above the base pointer. So here, let me, all right, got that fixed. Failing to use visual block mode there for a second. Okay, so what we've done is I've got the 10 now stored at address 24, and the value for I is stored at -4 above the base pointer. I really thought that it would just put the array first and then stash I. And for some reason, the compiler decided that it's going to put the primitive I at -4 and then the array. I don't understand. I expected to go the other way. All right, so that means I'm going to need to, this is the line I was really hoping to look at. It's going to take 24 off of the base pointer. So this is the address where I'm storing A0, and move it into a register. And then it's going to put the register, that contents of the register, into I, -4. All right, I'm going to try something a little different to see if I can get it to do the math and show you guys how that does the math. One sec. All right, got it. Okay, I made a couple quick changes to my memory. In order to make the compiler actually go ahead and do the math to figure out where an array location is, so I can walk you through this, I created a variable holding the index, and then I'm accessing my array using that variable stored index, and just going to store the result in X. So when the memory model, again, it went through and decided to put I at position 4 above the base pointer and X at 8 away from the base pointer. And then it put the array in, again, starting with the lowest address having the first element. So it looks like this. And then we take a look at this much right here. Those lines 10 through 14 are storing the array. This line is storing 2 in I, so that's going right here at 4 bytes above the base pointer. And then the calculation of the what value do I go get to store into X takes 2 lines right here. Okay, so what's going on? First thing it's going to do is it's going to go grab I and store it in a register. So I've got register, yeah, whoops. I cannot type today. I'm failing at typing. EAX is going to have I, which contains value 2. The next thing it's going to do is it's going to do a little bit of math. This 28 away from the base pointer is the starting address of the array. That's the element 0. So this much right here, it's in insert mode. Okay, minus 28 from EBP. This much is the start of the array. Okay, next thing I need to do is I need to offset. I need to go down 2 positions to get to A2. And that's actually going to be 8 bytes away. So what it's doing is it's stored number 2 in EAX, and it's going to use this scaling factor memory addressing. So minus 28 EBP, and then that index I is in EAX. So I'm just going to, yeah, do I want to write it like that? Does that kind of make sense? Next thing, it's 4 bytes per integer. Anyway, that I is stored in EAX. I'm going to leave it like that. That looks good to me. All right, and that's how I go and get the 30 out of that memory location. Let's see, it's right, there it is, 30 at 20 positions off the base pointer. And it's going to store that in EAX because I can't do direct memory to memory transfer, and I want to store it in X. X is, they've decided, the compiler's decided to store at 8 away from the base pointer, minus 8 EBP. And so that's what this last line right here does, is it just takes the value that we read from that memory and stores it in X. Okay, so this sort of addressing is designed for array access. It's the whole purpose of having this sort of memory access system is for arrays. All right, let me go grab my next topic and be right back. All right, I'm back. I just took an hour break for office hours. Not really sure it counts as a break if you're working, but something different. Trying to figure out where I left off, and it looks like I was about to do pointers. So let's take a look at this. Next example, this is going to be array4.c. I've got the same code I had up before, but I've added a pointer to that array. So this should point to address of A0. So here's the idea. It looks like, did I already do this? Yep, it moved the array up 1 more position to make room for that pointer, so that we've got the base pointer, then we've got I, X, and A, I, X, and A. So those are in the right order that we've declared them, and then the array was stacked on top of that. So let's take a look at the code here. Here I'm reserving space. Here I'm storing the array. This is storing 2 in I. So I is right there, 4-way. Then this is doing that math that grabs A of I and stores it in X. Right there, this is going to store it in X. X is at minus 8. There's the minus 8. All right, the next thing we're doing, the rest of this from line 19 down, is declaring that pointer and storing the address of A in the pointer. So here's the idea. It's going to use the load effective address. So quick hint, if you're looking at things that are directly reading values, accessing the data, it's going to be a move L. If it's a pointer, your clue is the LEA, load effective address. It's not foolproof because the compiler really enjoys using the load effective address to just do math. It's a very efficient way to do math. So not foolproof, it's not guaranteed to be a pointer, but if it's a pointer, we will need this. All right, so here's the idea. First thing I'm going to do is, this example is just going to store the value, the address of A in P. So it's going and getting the address, in fact, a 32 above the base pointer is A0, and it's just going to store that in a register. Okay, I can't move memory location, one memory to another location without going through register, so it has to put this in EAX. The next thing it's going to do is it's going to take EAX and put it in the location of the pointer, which is 12 above the base pointer. So it's storing the address of A, and this is pointer P. There we go, something like that. All right, that wraps up this example. I want to do one more little thing here, just to make this a little more interesting. I'm going to add a plus I right there. So I is stored value 2, and then I'm going to recompile this. We'll take a look at it. So first, if you guys have never done this directly from Vim, a little shortcut, I'm going to write this, and then I've been compiling several times, so I've already got this stored in here. To run a shell command, like the compiler from within Vim, it's a colon, exclamation point. And then I can just put in whatever compiler command I want right there. So I'm using gcc-s array4.c and all the rest of my options. And I've been experimenting trying to figure out what makes a great example. So if I just run this, it takes me to the command, tells me that, oh, file for the assembly has changed. That's because I just recompiled it. And so I can L for load the file. So I'm going to do that, L, and then I pull that up. And now it's actually changed down here. So let's take a look at what exactly changed. Let me find my spot. So there's the array stored beginning at 32. There's I. There's me doing some math to store x at -8. And then this is -4. Okay, so this is grabbing. All right, right, yeah, so this is where we are, line 19. So what this is going to do is it needs to compute the address of a plus I. So at I is 2, a plus 2 is going to be that data right there. So the first thing it's going to do is it's going to go get the value stored, this 2 right here, stored at -4, because this is I. So let me just make a comment over here, get I. All right, the next thing we're doing is we're going to do some math. So this load effective address, the compiler knows that these are all integers. And so to move 2 positions down, right, I can, in C I just wrote it like this, a plus I, and it takes care of all the details about the size, whether it's a char, which is a byte, or a short, which is 2 bytes, or an int, which is 4. It knows that I need to move 4 bytes per integer. So it's just going to do that math. So this load effective address is going to say take 0 plus, and then this is nothing in front of the comma, and then this is that scaling factor. So this is I right here. EAX is I, and I multiplied by 4. So this is just going to do 4 times I to get the number of bytes. All right, and it's going to store that in EDX because we're about to use EAX for the address. And what it's going to do next is it's going to go -32 EBP is right here. That's the address of A. Okay, it's going to store that in EAX. And then we're going to do some addition. It's just going to add, this is the number of bytes that we need to shift down from EAX, which is the start of A. Okay, and once we have that, it's store that this address. This is now the address of A2. It's going to store that in EAX, and then I'm going to move that into the pointer. So this pointer does have an address right there at -12. -12. This is storing the address in that memory location. All right, and then this is just my return 0, starting right there. All right, so I think just if I were to make a comment, if I wanted to sum up, every time I have A of I, that's really the same thing as, what's a good way to write this? A plus I, let's use lowercase. But when I do this, I need to dereference. So this is a good way to, an alternative way that I can write this. Every time I've got an array access, like this A4, I could say A plus 4 with a star to dereference it. And this is essentially what it's doing inside the compiler. It's figuring out, in this case, on the inside, so this is my C version. In assembly, I need that address of A plus 4 times I, because the array is an array of integers, and I need a 4. So it's going to compute this 4 times I first. Right, so we got I, multiplied it by 4, using the LEA to do math this time. Then we actually used LEA to grab an address because I needed the starting point for A. And then we put those two together. We just added A plus 4I and stashed that at the location of the pointer. All right, guys, I've got a 2D array example pulled up here. So here's what we're looking at. In main, I'm just declaring an integer array with 5 rows and 3 columns. And then I'm putting together this matrix. So 11, 12, 13, 21, 22, 23. So I've basically got row and column information as my numbers that are generating the matrix. And then if we look at the not commented code, I'm just putting these numbers in just manually to get this array. So I wanted to be able to look at the assembly and decide where it's putting everything. What's it doing? I originally tried this loop here to just fill in all the numbers. And with all the loops and the jumps, it just was too difficult to follow to just see where things were going with this array indexing. And see, it's actually really straightforward what we're doing. Let's take a look at the assembly code right here. So first thing we've done after we've set up the stack is we've reserved space for 64 bytes. Okay, I've got 5 rows of 3 integers each. So 5 times 3 is 15 total integers I'm going to be storing. They're 4 bytes each. That means I only really need 60 bytes. It's reserved 64 because it enjoys using multiples of 16. And then as I go through this, I'm just putting in all the numbers, and this is showing me the exact address where it's choosing to put element 0, 0. So I can see that this one is actually going in minus 60 from the base pointer. The next one down is at minus 56 from the base pointer. Okay, you get the idea. The next one is this one's minus 52, and then it does the next. So basically, it's creating these rows. It's keeping the rows together, and then it's got basically in a row. It's an array of 3 elements in an array. That sounded confusing. Yeah, so I'm going to just chunk this into 3 pieces. This goes first. Here's the second element. Here's the third element. It happens to have 3 numbers. The fourth element of an array happens to have 3 things. And the fifth element happens to have 3 things. And it's just going to put these down into memory. Let's see. I'm going to skip the middle, but we'll take a look. The 53 goes into 4 above the base pointer. So I'm going to do minus 4 base pointer. This one is going to be 8 from the base pointer. So like that. It just reserves a block of memory. It's going to store these in there in this arrangement. Okay, so next thing I want to do is actually let me write some code. One sec. There we go, some code written. What I want to do is demonstrate how the compiler is going to go through and figure out, using some math, the calculation it does to figure out which piece of memory, how far from the base pointer a particular address is. So I'm just going to grab, and I'm using variables here 3 and 1, so that when it gets to this line, it's actually got to do the math. It doesn't automatically just know where things are. If I hard code this, it'll just look up that line directly. Okay, so I didn't write this, and I didn't compile it. There we go. So this should tell me that I need to load the new version. Oh, made a horrible mistake. Timeout. What did I do? That was dumb. I'm an idiot. These all need to be comments. Otherwise, it tries to compile them. Make it look good. There we go. Okay. Now I write. Now we compile again. In fact, it even I didn't read any of the messages. All right, we'll load the new one. Enter to continue. And here we go. All right, we're in business again. All right, I just want to talk a little bit about the math that it's doing to compute where to go get a number to store an X. So 3,1 is going to be right here. It's number 42. So that's going to be row 0, 1, 2, 3, column 0, 1. So that 42 right there is the number we're going to go grab. All right, and again, if we take a look at this, minor change. It's gone ahead and reserved 80 bytes. And again, it enjoys multiples of 16. So 16 times 5 is 80. And it's also reserved space for I, J, and X. And it's putting those at the minus 4, minus 8, and minus 12 positions. And so the whole array got shifted by 12 bytes. So the top value is now at 72. And then this will be at 68. And the bottommost value of the array, I stored the 53 in minus 16, oops, wrong mode. Oh dear. Insert mode. Minus 16. There we go, and this will be minus 20. Okay, so the array is shifted a little bit in its position to make room for I, j, and k. And I is going to be stored at position 4, ABP. J will be stored minus 8. And X will be stored at minus 12. Hoping I got that right. I'll fix it if it's not when I go through the code. All right, so we've got the array stored here. The next thing we're doing, beginning at line 25 here, I'm going to make a little break here and divide this into some sections. So we're going to be computing where basically the address to go look up to store an X. And I've got 3 and 1 here. So the first thing I see is that I've got I stored with an immediate value of 3 at minus 4. Yep, so I did get that address correct. I'm putting a 1 in J, which is stored here. So this, if I just comment some of this stuff, this is I, and this is J. Okay, the next thing we're going to do is we're going to go and grab I. So this is I, this is where I is stored, and we're going to put it in EDX. Okay, now the calculation that we need to do is to figure out how to get from this address, the very first address of the array, all the way down to 3, 1 right here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 positions away. And what it's going to do when it computes this is it's going to take I times 3, because I've got a 3 right here. For every row that I'm going to go down, I need to advance it by 3 integers. So I times 3 is going to get me from A00 to A30. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Right there. That's advancing 9 positions. I think I counted the first one. My mouse in the wrong spot. And the next thing I'm going to do, once I get I times 3, then I need to add J to it. And then I need to figure out how many bytes to move. So this whole thing is going to be times 4. Kind of like that. Need the parenthesis. Does that look good? Extra parenthesis. There we go. Okay. So the first piece of this is going to be computing I times 3, because there are 3 integers per row, and I'm advancing I rows. So I know I've got 2 3s. This probably would have been a better example if I didn't have quite so many 3s involved. But here's the idea. So the way they're doing this is first they go grab I. Get I. And in a couple of statements, I times 3. All right, so first thing it does, it's going to make a copy in EAX. So EDX and EAX both contain the number 3. Then I'm going to add EAX to EAX and store it in EAX. So that's 3 plus 3 is 6. So now EDX has 3, EAX has 6. Then we're going to add those together. So D and A, 3 plus 6 equals 9. All right, now looking at this thinking, a normal human would never have decided to do it this way. But moves and adds are very efficient. It knows that it needs to get to that 3. That 3 is hard-coded right there. And so the compilers decided this is the most efficient, fastest way to compute I times 3. And so 3 times 3 is 9. And that's what we've got right here. All right, the next thing it needs to do is to go grab J and add it to that 9 right there. So J is stored at 8 bytes away from the base pointer. So it's going to go to that memory address and just grab that and store it in EDX. And then it's going to add EDX to EAX. So the result of that 9 was stored in EAX right there. So let me see here. If I'm commenting, this is going to go get J. And this is going to say 3 times I plus J, which equals 10. All right, from there, I'm ready to go to get the number from the array. So this first piece of this, the minus 72% EBP, hold on. Did I not renumber these? Made a mistake. All right, that was minus 72, and this is going to be, oh, what is it, 68? Could have sworn I changed that. Okay, right. The very beginning of the array is at minus 72. And this is going to move. So there's the start of the array. EAX is currently got 10. That's because I need to move down 10 numbers. But they're 4 bytes each. So this says multiply that by 4. So EAX is the offset times 4 bytes. And this number here is in, depending on the kind of array. If we're looking at an array of characters, this will be a 1. If it's an array of shorts, it'll be a 2. If it's an array of larger data, it'll be a bigger number. Your choices here are 1, 2, 4, 8. And it's just going to, so start at this position right here, minus 72, where the start of the array is. It's going to note that it needs to move 10 times 4, or 40 bytes, to get to this position right here. And then it's going to store that as I asked it to in X. So X is at minus 12 EBP, right there. All right, so that's all there is to it. It did take a bunch of weird steps in the middle, and the compiler is going to know how to most efficiently compute where things are, and it does take a whole bunch of different kinds of optimizations that are available to it to figure out how to do this as efficiently as possible. I mean, it knows how long it takes to execute each instruction. It chose not to multiply, because multiply takes like, I don't know, 30 clock cycles on the CPU, and addition takes 1 to 2. It knows that this is a faster way to get there. All right. Let's see here. Right. A couple of things. I want to talk about a little bit about things that you can do to optimize your own code. So, yeah, let's see here. One of those things is by using hard coding as much as you can. Like, I mean, C allows me to use variable sized arrays. That's new since the C999 standard. Was it ISO 99? Something like that. It does let me use variable size arrays, but the math to access elements of variable size arrays is very much slower. It needs to do a lot of multiplication and to figure out the address of things. But if I can use a fixed size array, so basically I don't want to put a variable here, but if you remember, I can define, no string on the cursor. Come on, insert. There we go. Define rows. I'm going to say rows are 5. Define columns as 3. So if I go ahead and do something like this, and then I can just replace this, because this hash symbol is a pre-compiler directive that just says this is a variable that I'm using in my code, copy and paste the 5 everywhere. This is going to hard code a 5, but let me still use a variable so that I can like make changes to it easily. So this sort of structure where we're using hash defined constants is a great way to just make sure things are hard coded so the compiler knows exactly how big they are, and it can do the most efficient possible math. We'll also find that the compiler has, let me see, where did I put that stuff? I'm looking at my notes on the other screen. Okay, there's a bunch of different compiler options too for changing the way that, let me just pull this up. So this was the string I used to compile things. A ton of options. I can add dash, let's see, what is it, capital O0 to say do not optimize anything. It's going to compile very quickly. It doesn't have to think very hard to do the compiling. It just takes each line, turns it into whatever steps. This is very useful for making the debugging process easier, and this is the default mode. If you ever want to write code that goes faster, then we've got 3 more choices. If we add that's supposed to be a dash, not an equals. I apologize. Dash capital O1, then the compiler is going to use this to try and reduce the size of the code and make it run faster. But it's still going to skip any of the optimizations that take a long time to compile. So it's still going to compile quickly, but it's going to produce more efficient running code. And it might do things like unwind loops. You know, if I were to actually initialize my, let's see here, my code with the loops here in lines 6, 7, and 8, it might choose to instead just copy and paste this in because it goes faster than having to keep track of loops and uses less memory on the stack. Just as an example. If I go back over here, level 2 optimization is even better. It performs nearly all of the supported optimizations that don't involve like a space, speed, time trade-off. So it definitely takes longer to compile than 01, but the performance of the generated code is likely to be even better. And there's a third level too. Level 3 basically turns on every single possible optimization that is available. It may take a long time to code, a long time to compile, but it's going to give you the most efficient possible code that the compiler is capable of generating. But again, I'm not going to use these for this class because it makes the assembly really hard to read. So we're going to go with the default for when I'm working here. Okay, let me think. What else was I going to talk about? Yep. Oh, right. One more thing. So the variable size arrays, that just means that I can use, maybe I wasn't clear on this. Let me get out of here. A variable size array would mean like, here, get I from user, and then we'll declare b to be of size II. So it's going to let me do that. But some of the problems are when I start doing the math to compute where addresses are, it's going to have to actually do multiplication. It's not just going to know how to get around with here, it's using addition instead of multiplication because this is faster. It's going to straight up just do the multiplication. It's going to slow it down. And modern CPUs, like the Intel processor we're working with, only have a limited number of registers. And so if I'm using a loop to access all of the, just loop through all of the elements in an array, it may run out of registers as it does this computation and have to go to memory to store things that it would have just retained in a register. And so that extra memory access every single time through a loop can also make these variable size arrays very slow. So my advice is to avoid them if you can. All right, this is going to wrap up arrays for me and rambling. I think the rambling was sort of on topic and useful, I hope. So I'm going to leave it in. I'm going to go prepare my next set of examples as we talk about structures. Be right back. All right, guys, that was a little bit longer break than I planned on taking. I had to drop my son off at his mom's, and then I got in a workout, but I'm back now with my struct example. All right, so here's what we've got going on. I've just got a struct class here, not a class, a struct that it's got a bunch of pieces of data. So I've got an integer x and y for the point coordinates. I've got a name if I want to give it a name, and a symbol if I wanted to, put this on a graph and use like a star or a period or whatever it is. I'm going to record what symbol I'm going to use. And then I tried a bunch of stuff trying to figure out what's going to be the easiest way to explain how C is going to turn structs into assembly code and how they are stored in memory. So I started off with version 1 here. I'm going to come back and pull this up in a second. This was fascinating. And then I thought, I'll just do it this way. I'll just x is 0, y is 0. I'll name it origin. To copy a string into another string, I just use my string copy. This was fascinating too. I've never actually looked at the assembly code for this. I've used this on exam questions. I love this string copy. So I want to go and just talk about this for a minute. Sorry about that. Forgot to mute that. Do that now. Good. All right. I'm going to come back to this, but I wanted the easiest possible version of a struct so we can just see what it looks like. So basically what I've gone and done is created version 3 here. I've got a point. I'm assigning each of the individual characters and values, and a number. X is going to be 0, Y is 0. This is going to be the origin, and my symbol here is going to be a star. So I'm just putting in everything individually as simply as I can possibly do it. And now I want to see what assembly comes up with to store this in memory. How is it doing it? All right, so we take the first 2 lines of the assembly. This is just stack management stuff. And then we go in. This is going to reserve the memory. Make some space. Reserves. All right, reserve the space in memory. Okay, it's reserving 32 bytes. Let's take a look at what we really need to store this struct. Okay, the x here is an integer, so that's going to be 4 bytes. Y is an int, that's another 4 bytes. So we're up to 8. The character array for the name has 12, so 8 plus 12 is 20. And then the character for the symbol is 1 more byte, so that's going to be 21 bytes total. And again, C enjoys reserving multiples of 16 bytes, so that's why they chose 32, when we really only needed 21. Okay, now check this out. So here's what's going on. This next line is going to move the 0 into x. So it's storing x at 24. So it's got some extra space. It didn't choose 21. Anyway, I've got my little picture of memory here. I've reserved 32 bytes on the stack. At byte 24, I'm putting in a 0 for x. And then, oops. Focus mic. Type in the right spot. There we go. Same deal for y. At 20 bytes below from the base pointer, I'm storing a 0 for y. And then I've got all the numbers here for the ASCII values of the characters. Let me just pull this up real quick. So I went ahead, I grabbed the manual page for ASCII and just looked up just to check. Like the first number was 111 in decimal right there. So that's lowercase o. That's the O in origin. Now let me get rid of that for a sec. So 111 lowercase o for origin is at 16 bytes from the base pointer. So I've got the O right there, then the R, G, O, R, I, G, I, N, and at minus 10, right there we're storing 0. That's the \0. Okay, so I've got this string stored right here in memory. And then the next thing we do, check this out, I want to just point out that I reserved 12 bytes for the name. In a second, I'm going to come back and change that and have a look at how this changes. I'm going to leave it at 12 for a second. And then the last thing I do is store 42, that's the ASCII value for the star, at minus 4. So it's doing everything it can to pack the struct into memory, just all of the pieces of the struct, the X, Y, name, symbol, they're all in order. And then it didn't actually move them down all the way to start at minus 1 from the base pointer. There's 3 empty bytes right there at the end that are not used. And part of that reason is alignment. So one of the things that C enjoys doing is, the compiler enjoys doing, is lining up the values of integers with things that are divisible by the size of bytes. I'm sorry, for any data structure, for any of the primitives, it's going to take that size and make sure that wherever it starts putting it, whatever byte it's putting it on is divisible by that number. So maybe an example, if I have an integer, I'm looking for memory addresses that are divisible by 4 because it's 4 bytes. Okay. If I'm storing a short in memory, then I want integer addresses that are even because those are divisible by the 2 bytes for the short. All right, I hope that kind of makes sense. If it's like a long, those are 8 bytes, it's going to start storing them at memory locations that are divisible by 8. And so that's part of the reason that we put the X here at 24 and why there's extra empty space at the end. I've got 3 more bytes that I haven't used. All right, real quick, I want to go through a couple little changes and talk about some other things. So basically, to sum up, it's going to store structs in memory. It figures out how much memory it needs. It's going to take all of the pieces of data and make sure that the alignment problems are solved. So an integer like x is going to start on something divisible by 4. This is an integer, it needs to be divisible by 4. The characters need to be divisible by 1, so pretty much anywhere. And then extra space at the end. because of this alignment. They want everything to be as contiguous as possible in memory. All right, now one of the things I want to try is just a little experiment here. I'm going to go ahead and change. So I reserved 12 bytes. That made this nice and neat and let this fit at -4 for the star. What if I change this to 11? All right, so I've changed the number of characters in my name to 11, the name string here, and recompiled it. And I'm taking a look at the code. First thing I notice is that the very first position where I'm storing the beginning of the struct is now at -20 instead of -24. So here's the old one. It was at -24 from the base pointer. So check this out. So an integer takes 4 bytes. There's another 4 for y. That's 8. And then the symbol is 1, and the name is 11. So 11 plus 1 is 12, plus 8 is 20. So the whole thing now takes up exactly 20 bytes. And so we see that we are starting at 20 bytes for x, 16 for y. Then it's going to put the string in origin, null terminal character. And then it's going to reserve, there's a bunch of blank spaces that are not used for the word origin. And then the star symbol is now stored at -1 from the base pointer. So it exactly packs into 20 bytes here. I'm going to make one more little change. What if this weren't 11, but instead 10? We'll save that. We'll compile it again. We'll load the new source assembly code. And now we've got 19 bytes worth of data. And I'm curious, I want to know whether it put the symbol at byte -1 again and saved that blank space after the name, or if it actually moved it up. Let's see here. So I need that 42. It's right there. 42 is the symbol for, or the ASCII code for star. And check it out. It actually put it at -2 and left one blank empty byte at the end. All right, and again, that's all because the alignment, the very first integer needs to go on something divisible by 4. So we're looking for, right there, that 20 divisible by 4. All right, next thing I want to do while I'm cruising along, I'm going to set this back to 12. I'm going to keep it there so that when you guys come and you look at the code and like are trying to follow along with the lecture, it's already set up with everything you need. All right, so what I'm going to do now is I'm going to look at some of these other versions. So I'm going to comment this out. And then we'll try turning some of these on. So let's take a look at this one where I'm just using this, what's it called? Array initializer, no, struct initializer string. We'll save it. We'll compile it. We'll load the new assembly code, and we'll have a look. This actually comes in very short. This is the most efficient way to do this as far as how many assembly instructions are required. But because the compiler already knows that I've got this string here, it's shortening this up. All right, so I'm back to reserving. I've got 32 bytes. I'm starting at -24 for x, -20 for y. So this is the exact same memory model that I've got over here, the original one. But then what it's done is it's actually packing in the first 4 bytes worth of characters, ORIG. And here, this is the, if I take all 4 of those bytes in ASCII, store them in memory, and then convert that to a decimal value, this is that decimal value. So it's doing a whole bunch of math. So it can shorten this much, those 4 letters, into one statement right there. Kind of cool. I kind of like that. They're collapsing things down, making them a little wait, these 4 letters. Well, I'm pointing at the wrong spot. Same 4 letters, but and then the next thing we do is we've got these bytes, IN, the null terminal character 0, and the spaces we're not using. It's just packing those into one integer and packing in and then storing those. Then let's see, we've got, the rest of this string is just going to be packed with zeros. Normally you wouldn't see this happening. I was kind of surprised about it. And then the 42 is the star character, and that's going to be stored in 4 from the base pointer right here, just like we had before. So in this case, this 8 is getting packed with the value 0 right there. All right, cool. I'm going to again return this to, so that when you guys download this and are like watching the video for the first time, there's nothing there. It's normally it's not, you know, when I did this version, I didn't do anything specific to overwrite that 8 bytes from the base pointer. This version took care of it. It filled it in with zeros for me. So awesome. Okay, next up, I want to talk about this version right here. The one where I'm using my string copy function. I just want to like take a look at the assembly for that because this was fascinating to me. So one sec, let me save this. We'll compile it again. We'll load the new assembly, and we're back. Okay, so this is basically doing the same thing we had before. I'm creating space for a new point, struct. It's again reserving 32 bytes. And then we've got store 0 in minus 32. Now check this out. Before we were storing it at minus 24. Now for some reason when I do this, and I don't have a good explanation for it, it's decided to store it at minus 32 from the base pointer and minus 28 from the base pointer. All right, now this string copy, I just want to just highlight a couple of things. In the code, there's like a code section at the top, then there's a section for global variables, and that's where the word origin is stored. So I can see right here at label.lc0 colon, that colon means it's a label. I'm storing a string right here. And so that's what this line right here is doing, is it's taking this memory address, the minus 4. Oh, wait a second, I'm dumb. I know exactly why we're using minus 32. Hold on. It's because I declared 2 pointers right here, S1 and S2, and it's storing those at probably, what do we got, minus 4. Yep, minus 4 for that one and minus 8 for that one, and that's why it moved up by 8 bytes. All right. I apologize. My brain wasn't working there for a second. I'm just being dumb. Okay, back to what's going on with the string copy. So I'm storing this origin in the global variable section where I've got all of that kind of information. Things that are constant, things that aren't going to change. It's in the .text section is what it's called. So anyway, that's where this is. It's stored at .lc0 in memory, that label. So I'm moving that address into the address where I'm, you know, it's what's it called? A pointer. I got this. Here, let me just make myself a note. This is S1, which is a pointer to the origin data in memory. Okay, next thing I'm going to do is I'm going to grab the address where I want to write this and store it in S2. So S2 is going to be right here at 8 bytes from the base pointer. So that's going to be S2 pointer to, and this is going to be the name part of P0. Yep, right there, P0.name. So that's what goes right here. And the way we get that is we start with the very first byte of the struct, which is 32 off of the base pointer. We're going to stash that into EAX. And then the way C works with structs, it just remembers how far from the very first byte, which is right there, each of these things are. So X is 0 bytes away, Y is 4 bytes away. The name is going to be 8 bytes away. The symbol here is going to be, what is that, 21 bytes away. All right, so that's how it works. It just remembers how many bytes are offset from these guys. All right, and so that's what it's computing right here. Here's the starting address. That's where the X is stored. And then it knows that it needs to jump down by 8 bytes to get to the very first character in the names. And it's going to store that in this memory location right here. All right, now check out this loop. It also knows that it can go ahead with this loop because the very first time through the loop, it's going to pass. It knows what's in here. It knows that the very first were, this is not 0. So it can get away with using this do while style loop. And the very first thing it does, and I've got the EDX register highlighted so we can see where this is used. It's going to grab that value. So 4 away from the base pointer is S1. So it's going to grab S1, which is the pointer to somewhere, and store that in EDX. The next thing it does is it's going to increment that and store it in EAX. So in my string copy function here, the way this works, it's going to take a pointer to the very first character, the O in this case, That'll be S1 points there, and S2 is pointing to the very first character here. It's going to copy that character over using this assignment operator. Then it's going to increment both of these, okay? And then it's going to look and see what was copied. If it was a 0 or that null terminal, then the loop will end. Otherwise, it's going to go back and do the same loop again. All right, so here we're actually doing the increment before we do any copying. So right here, this is S1. We're incrementing S1, but we're going to store it in a different place. So the actual value that I'm about to copy in, the location where that's going is EDX. The new incremented pointer is going in EAX. All right, I hope that made sense. So I'm incrementing first, but I'm not overwriting that value yet. I'm just storing it somewhere else. And then the next thing I do, take that incremented value, and I'm going to store this in memory. So EDX is the pointer to the character I want to copy, and this is the first step of the increment. I just added 1 to it. Then I'm storing it back in S1. Okay? And then I do the same thing here. This is the E8 away, so this is the S2 pointer. I'm going to increment it, make a copy, keep that in E. I'm keeping the original in EAX. The new incremented pointer is in ECX, and then I'm going to store this back in memory so that S2 now points to the second character. And then this code right here is just going to take the, remember EDX is where the O was, the O in origin. It's going to take that byte. Let's see, don't get ahead of yourself, Mike. Yep, it's gonna look up that memory address, go get the data there, and then it's gonna grab the first byte of that, the lower 8 bits, move that into EAX. Wait, I'm afraid I said that wrong. It's copying that one character. This is with the parentheses. This is not the register. This is the address the register is pointed to. So this is going to be the P0 name character 0 right there. Okay, and now I've copied the character. The next thing, this part is all about the test because this is a while loop. This is a conditional. So what I need to do is go grab the character that was copied. So the return value of an assignment statement like this is whatever was copied. So it's going to go grab the memory contents of that copy, put it in EAX, and then it's going to test to see if that copy is equal to 0 or not. So it's just going to grab the lower 8 bits and see if it's not equal to 0, then we jump back up to L2 and we do this again. As soon as it's equal to 0, we are done with the copy. Then to wrap up, this is the star and the return 0. All right, so yeah, in assembly, this is actually, it's kind of complicated, and I've never actually seen this before. I thought it was fascinating, and I wanted to walk through and share what's going on with you guys. For like a do-it-yourself, try at home, try coming up with a loop that uses a counter, for I equals 1 or 0 to however many characters there are, and just see if this code right here, this loop, from there to there, and there's some setup where we made the pointers. Let's actually be a little more accurate. Yep, S1 was there, through there. How many lines of code? 16 to 30? So that took 16 lines of assembly. Is using a counter variable with a for loop or a while loop with a counter that gets incremented more or less efficient? See if you can come up with a better version than this. All right, guys, that'll wrap up what I want to do for structures. Next, I want to talk about just a little bit about security. This seems like the best place for this. And I've got a little example here of things that can go horribly wrong. This is a buffer overflow attack, or vulnerability, or just me being dumb writing bad code. Here's the idea. So I've got a main function that just calls f. All f does, f is actually the same code that we saw from array1.c is my very first example. I'm just declaring an array with 5 numbers, 0, 1, 2, 3, 4, 10, 20, 30, 40, 50. But then I'm out of space. And I've gone ahead and I've added 2 extra numbers to this anyway. So when I did array1.c, I saw that at 20 bytes from the base pointer, I was putting a 10, 16 bytes of 20, 4 bytes down here of 50. I've got those just stored in memory. But then below that, at 0 bytes, at actually where the base pointer is pointed, we have the stored base pointer for main. And below that, we have the return value. So this generates perfectly good looking assembly code. There is nothing that's going to stop me from writing to data that's not actually part of my array. So here's the idea. The compiler just goes along and does exactly what it's told. It's going to reserve memory. It's going to make it a multiple of 16 and grab the base pointer, do the stack stuff, reserve space for my array right there. It's going to store the 10, 20, 30, 40, and 50 at the locations. It knows exactly how much memory it needs because I told it. Right there, save space for 5 integers. That's 20 bytes. But then I wrote to places out of bounds. So this fifth one, it still does its just normal computation to figure out where A5 is, and it knows that it is 0 bytes away from the base pointer, which is where the base pointer is stored. So I just overwrote my base pointer with 0. That's that like reserved special memory address that you can't actually access. I just stuck it in the base pointer. So when we return, it'll restore that the old base pointer from main to point to this invalid address. And then the next thing I'm doing is in A6, this is actually where the return value is stored, right here at 4 bytes below the base, or above, 4 bytes above the base pointer. I'm going to stick a 0 right there too. So this is going to take the code and return it to, this is supposed to store the value of the next instruction to be executed. It's going to put this to this special reserved, can't execute, can't do anything with the value. And then it's just going to return. All right. So, and then main just sets up the stack, calls F, and then tries to return 0. So this is the setup for return 0 right there. All right, this compiles. This is the code I generated. I'm going to get out of here for a second. Quit all. We'll go up. We'll compile this. This is what I'm using to compile GCC. Buffer1 is my example name. I've got all of those same options turned on that I used to generate the assembly code. So we'll run that. If I don't give it a -o with the name of the file, it just creates a.out as an executable. That's the default name. So that's what I just created. I'm going to run that. And this will generate a segmentation fault because as soon as it gets to the point where it's trying to return from that function, it can't. I've completely overwritten the return value. The base pointer is messed up. This is totally going to crash. So let me pull that code back up again. We'll just leave this screen available while I talk about some of the things people do to basically as a security vulnerabilities. This is a really common way to attack other people's servers or other people's programs. If you ever have the opportunity to enter a string as a user and you enter a string that's longer than they reserve space for, because of the way the arrays are stored, basically as you continue to add more and more data, it is marching closer and closer and closer toward the base pointer and the return value. So if you just put in more data than they have actually allowed space for, you can overwrite the base pointer and return value. And that lets you take control of their computer because you can now have the code return to basically anywhere you want to. And if your string has enough space, you can actually put in executable code in binary as your string, overwrite the return value so it jumps to your executable code and attack their computer. And frequently that's just code that will execute a shell command to enable another vulnerability or something like that. So I just want to talk for a second about, this is a sales pitch for computer security. That's actually one of my favorite classes. I love it. I highly recommend it. One of the homework assignments is to write a buffer overflow attack, just like we just did right here, where you actually get to tailor the string that you're putting in as the user so that it overwrites the return value and has executable code that you can take advantage of. But anyway, there are a couple of things that modern computer systems do to help protect against buffer overflow attacks like this. Our book talks about 3 of them. There's lots of things that people do, lots of ways to security experts try and protect things. The ones in our book, stack randomization is the first. Basically, when we start a brand new program, like when we call main right here, I've been using that -fno stack protector. The fno means turn off the stack protector. What this would normally do is it's going to just insert a whole bunch of bytes, a random number of bytes before main. so that the address values where things are going to be unpredictable. So it makes it hard to know exactly where I'm going to jump. The return value for main, right here when I return, the return value is stored right there on my function. That's going to try and jump back to main. If this is a predictable location, then when I overwrite it, I know where to jump to get to my code. If I know that everything has been shifted up or down, it makes it much more difficult to predict exactly where I want to jump to. All right, so stack randomization is the idea that I'm just going to add a whole bunch of empty bytes before main so that these memory addresses here, right now, they're all in terms of registers, they're shifted, but in the binary, it's going to actually be using real values for the memory locations. They'll be shifted a little bit. Okay. All right, so the next thing we're going to do is called a stack protector, or a guard, or a canary. This is basically a special value that's put on the stack right after the base pointer. So we store the return value, we store the base pointer, and then we put in a canary value. So canary, I can spell. And that's named for the bird that you would take into a mine, and if there's like a gas leak or something, the canary dies, and then you know that the air quality is bad. So canary or guard would go right here in the code. The idea is that, and this only happens for functions that have a character buffer that's filled in by a user. So I need basically I need to have declared a char, star, or char array of some kind. And then it'll go ahead and add this canary value, and it's just a random value that gets stored right here. And before the function returns, before it actually tries to jump here, it just checks and verifies that the canary value is still valid. Because above that is my array, below that is the return value. If I'm overwriting things with my attack code, I will overwrite the canary. And if that number or that data has changed, I know that I've been attacked and I should get out, abort immediately, don't execute any code further. So that's the idea behind that. It's incredibly hard to guess what the canary value would be if I'm attacking. And go take computer security. You can learn how to get around that. Amazing, fun stuff. All right, and finally, the final thing is more built into the actual CPU itself. And that's going to say that only certain regions of memory are allowed to hold executable code. So there's just a bit that's associated with different pages in memory that says this can be executed, this code can actually contain code, and this part can't. So we don't want to execute any data that's actually written to the stack. The stack should never contain executable code. That should be in the code section up at the top. We have code, we've got global variables, we've got the heap, and then we've got the stack. The stack and the heap should never contain executable code. So it's just going to be a little flag, a bit that's in memory that says these pages of memory are available for code and these are not. All right, so I'm feeling like I'm rambling on a lot. It's a long video. I'm going to wrap it up right here and get this process put on YouTube, and then it's actually getting kind of 8:23. I'll probably get started preparing my notes for the next one, but it probably won't come out until tomorrow afternoon. So anyway, with that, have a great day, guys, and talk to you soon.